afternoon to one and all. This is Dr. K. Pushpa Rani, Associate Professor, Department of CSE, MLR Institute of Technology. In the last video, we already discussed about the recurrence relation using substitution method. Now, second method for recurrence relation is generating functions. There are three methods to find the solution for the recurrence relation. First method is a substitution method. Second one is a generating function. Second method and third method are very important for exam point of view compared to the substitution method. Substitution method for like a short answer question, but generating function characteristics or characteristic roots are long answer questions. So in this video, we'll discuss about what is a generating function, what is the procedure to find the solution of the recurrence relation using generating function, and we can understand that concept by considering some examples. So what is the method of generating function? Recurrence relations can also be solved by using generating function. But before solving the problems using generating function, we need to remember some equivalent expressions. Suppose the generating function a of x is equal to sigma n equal to 0 to n a n x to the power of n is the generalized term for the recurrence relation. Suppose if it is a term has to be expanded, then what is the formula? N is equal to k to n a n x n. If it is a nth term, then a of x minus a naught minus a1 x minus a k minus 1 x to the power of k minus 1 is the last term. The first term is a of x, last term is a of k minus 1 into x to the power of k minus 1. Suppose if it is a first term is an minus 1 x to the power of n, then we need to add x into a of x. X into a of x, last term will be reduced. If it is a nth term, k minus 1 is the last term in the sequence. If it is a n minus 1, k minus 2 x to the power of k minus 2 is the last term in the sequence, and we need to add x. Here the constant as 1, but here it is the constant as not a constant, it is the x term. The first term is a constant term, second term is the x term. Suppose an minus 2 x to the power of n, then x square, and it is a second term x square, last term will be reduced to k minus 3, a into k minus 3 x to the power of k minus 3. Then if it is a fourth term x cube, n minus 3 x cube. Then if it is a k term, x to the power of k, a of x is the last term. We need to remember all these formulas before calculating the formula for the recurrence relation. If it is nth term, then a of x. Then if it is n minus 1, x into a of x minus a naught minus a1 x, a2 x and so on, a k minus 2 x to the power of k minus 2. If it is a n minus 2 x square, and it is repeated up to the k minus 3 into x to the power of k minus 3. And if it is n minus 3, then we have to use x power 3 is the sequence. Then n minus k x to the power of k. So these are called as a generating function for the recurrence relation. Now let us consider one example how to find the solution using the generating function. So first of all, solve the recurrence relation. So an minus 7a n minus 1 plus 10a n minus 2 equal to 0 for n greater than or equal to 2. That means there are three terms. N is equal to up to, so t up to 2. That means second term. That is the second order recurrence relation. It is the second order recurrence relation. And the initial values of a naught is 10 and a1 is equal to 41. What is step number 1? Let a of x equal to sigma n equal to 0 to infinity a n x n. That is the equation number 1. That is the generalized term for the generating function. Second term is a multiply each term in the recurrence relation by x to the power of n and take the summation from 2 to infinity. What is the first term? A n. Sigma n equal to 2 to infinity, because we have to start n value is greater than or equal to 2. So n equal to 2 to infinity a n x to the power of n minus 7 sigma n equal to 2 to infinity a n minus 1 x to the power of n plus 10 sigma n equal to infinity an minus 2x to the power of n is equal to 0. That is step number 2. Multiply each term with x power n. So first term is an, multiply with x power n. Second term is n minus 1 term, multiply with x power n, and n minus 2 multiply with x power n, and take the summation from 2 to infinity. Step number 3. And we need to replace each infinite term with the corresponding equivalent expression. That means the first term an means a of x minus a naught minus a1 x. If it is a second term, an minus 1 means up to 2 terms, x7x into a of x minus a naught. Then third term, 10x square into a of x, that is equal to 0. Now we need to separate the terms. Now we need to simplify. So take a of x as common. 1 minus 7x plus 10x square is equal to a naught plus a1x minus 7a naught. A of x is equal to a naught plus a1x minus 7ax. Then this fraction will comes to the downside, 1 minus 7x plus 10x square. Then again we need to separate the constant term, x terms. A naught is only one constant term. Then from this we have to take x as common, a1 minus 7a naught into x. So on we have to find out the what are the fractional fractions. That is a 1 minus 2x, 1 minus 5x. That is a 10x square minus 7x plus 1. That is the x square term, x term, and t term. That is, then we have to find out 10 means 5 2 5 10x square minus 2x minus 5x plus 1. Take 2x as common, 5x minus 1 minus 1 into 5x minus 1. Then 2x minus 1, 5x minus 1. That means 1 minus 2x, 1 minus 5x. We'll get the two fractions. Now we need to decompose the fractional fractions by taking the constant term. A naught will be considered as C1 by 1 minus 2x, and second fraction will be, instead of taking all this term, we can take the C2 as a constant, where C1, C2 are the constant. Then we know that formal partial series is C1 by 1 minus 2x plus C2 by 1 minus 1 pi. That is, you can write it as a closed form of the generalized equation, C1 into sigma n equal to 0 to infinity 2 power n x power n, because 1 by 1 minus 2x is written as 2 power n x to the power of n. That is that is already discussed in the generating function sequence of recurrence relation, 2 power n. The same way, C2 has a constant 5 power n, 2 power n. So this is the equation. We need to remove this n, that is n equal 0 to infinity. We'll get C1 into 2 power n and C2 into 5 power n is the solution of the recurrence relation. This is the equation number 1. But in the question itself as given as a naught is equal to 10, a1 is equal to 41. So this is the base equation. From the base equation we have to substitute, put n equal to 0 in the given equation. That means in the place of n we have to substitute a naught equal to C1 2 power n, means n value is 0, plus C2 5 power 0, that is equal to 10. That is C1 plus C2 equal to a naught value is 10. That is equation number 2. Then after that, put n equal to 1 in equation 1. We'll get, so a1 equal to C1 2 power n means 2 power 1 plus C2 5 power 1, that is equal to a1 value is 41, 2 C1 plus 5 C2. We need to solve the equations 2 and 3. Then we'll get C1 is equal to 3, C2 is equal to 7. That is 2 C1 plus 5 C2 equal to 41. C1 plus C2 equal to 10. Then we need to multiply with the 2, that is equation 2, will get 2C1, 2C2, 20. and we have to subtract. We have to subtract means plus minus will get cancelled. That is 3C2 equal to 21 minus 20, that is 21. Then we'll get C2 value as 7. Once we know the value of C2, then what is the equation? That is C1 plus C2 equal to 10 means 10 plus 10 equal to C1 plus C2 is 10 equal to, that is C1 plus 7. Then C1 is equal to 10 minus 7, that is 3. So 3 and 7. Substitute these two values in the equation. 10 equal to C1 plus C2, that is 10 equal to C1 value is C1, C2 is 7, from this C1 equal to 3. So substitute C1, C2 values in the equation 1, will get the unique solution is an equal to C1 to the power of 2, C1 into 2 power n, C2 into 2 power n. C1 is 3 into 2 power n plus C2 is 7 into 5 power n is the solution for the recurrence relation using generating functions. Now consider the second example. Find the general expression for a given recurrence relation using the generating function. So what is the first term? What is step number 1? Let a of x is equal to sigma n equal to 0 to infinity a n x to the power of n. Second step, multiply each term by x to the power of n and take the summation from 2 to infinity because n greater than or equal to 2. So take the summation from 2 to infinity. Then what we are going to get sigma n equal to 2 to infinity a n minus 7 sigma n equal to 2 to infinity a n minus 1 x to the power of n into x to the power of n plus 12 sigma n equal to 2 to infinity a n minus 2 x to the power of n is equal to 0. Now we need to separate the terms in the fractional fraction, separate the terms and we have to find the solution. Then this term is written as a n x to the power of n means a of x. So according to the step 3, in the all the example we already discussed. So replace each term with the corresponding equation. The first term is a0 a1x, second term is a0, third term is just to only consider as a single term. Like that we have to apply the same thing. So that is a of x minus a0 minus a1x. That is the first term minus 7x a of x minus a1x plus 12x square. This is a not only 12x square into a of x is equal to 0. Next, we need to separate the terms a of x minus a0 minus a1x minus 7x a0 plus 7x a0 plus 12x square into a of x is equal to 0. Now we need to separate according to the fractional fractions. A of x, take it as common, 1 minus 7x plus 12x square equal to, so this term will come to the right side, a0 plus a1x, this term will be going to the right side, a1x plus, so that is 7x x, then 7x a0, this will be going to the right side, minus 7x a naught. Then a of x is equal to, take that constant a naught plus x is, take it as common, a1 plus that is minus a1 minus 7x 7 a naught by 1 minus 7x plus 12x square. So now we need to find the terms in the expansion, that is 12x square plus 12x square minus 7x plus 1. So that is 12 means 4 and 3. 4 and 3. 1 minus 12x square minus 4x minus 3x plus 1. Take 4x as common. 4 3s are 3x minus 1 minus 1 into 3x minus 1. Then 3x minus 1, 4x minus 1, that is equal to, so take the two constants, c1 by 1 minus 3x plus c2 by 1 minute. Then a of x is equal to c1 by 1 minus 3x plus c2 by 1 minus 4x. Then it is written as c1 sigma n equal to 0 to infinity. What is the generalized or closed form for 1 by 1 minus 3x? That is 3 power n x to the power of n. Same way for the generalized formula for 1 by 1 minus 4x is c2 into sigma n equal to 0 to infinity 3/4 power n x to the power of n. So that is c1 into 3 power n plus c2 into 3 power n is the solution for the recurrence relation an. If n value has given, we have to substitute those values and we need to find the solution for the recurrence relation. Next, consider the next example. So using generating function, solve the recurrence relation an minus 4a n minus 1 plus 3a n minus 2 equal to 0 for n greater than or equal to 2 using the initial condition. So what is step number 1? A of x is equal to sigma n equal to 0 to infinity a n x to the power of n. Next, multiply each term in the recurrence relation. We need to substitute. Okay, so multiply each term in the recurrence relation. Then take the summation from n equal to 2 to infinity. We'll get that is sigma n equal to 2 to infinity a n x to the power of n, first term, minus second term is 4 sigma n equal to 2 to infinity a n minus 1 x to the power of n plus 3 sigma n equal to 2 to infinity a n minus 2 x to the power of n equal to 0. Replace each term with the corresponding equation. Then we'll get u of x minus a naught minus a1x minus 4x into a of x minus a naught plus 3x square into a of x equal to 0. Then we need to separate the terms like a of x into, take a of x as common, 1 minus 4x plus 3x square. And take the remaining terms out to the right side of the equation, a naught plus a1x plus minus 4x a naught. Then a of x is equal to a naught plus a1x plus minus 4x a naught. And what is the denominator? 1 minus 4x plus 3x square. Then what is a of x is equal to, take the two constant, then 1 minus 4x plus 3x square will get, so c1 by 1 minus x is one term and c2 by 1 minus 3x is another term. Then take the summation according to the recurrence relation. That means take the decomposition of fractional fractions. Then a of x is equal to sigma, that is c1. So it is written as c1 into 2 power s, sigma n equal to 0 to infinity x to the power of n, that is c1 into x to the power of 1, that is 1 into x to the power of n, plus c2 sigma n equal to 0 to infinity. Second term is, first term is x, second term is 3 power x, that is 3 power n x to the power of n, that is c1 into 1 to the power of n plus c2 into 3 power n. That is the recurrence relation an. This is the equation number 1. So there is a initial conditions already given in the equation. A0 equal to 2, A1 equal to 4. You need to substitute the initial conditions in the recurrence relation of the solution of recurrence relation. So that is A0 equal to 2, A1 equal to 4. Then put n equal to 0 in equation 1. Then we'll get A0 equal to C1 plus 3, that is C2. That implies C1 plus C2 equal to 2. That is equation number 2. Next, put n equal to 1 in equation number 1. Then A1 equal to C1 plus C2, that is 3C2. That is equal to C1 plus 3C2 equal to, what is the value? 4. That is C. Next, we need to find the solution of recurrence C1, C2 values. Then solve equation 2 and 3. Solve equation 2 and 3. We'll get C1 plus C2. Here we can find C1 plus C2 equal to 2. Then C1 plus 3C2 equal to 4. Now we need to subtract here, minus, minus, minus. Then we'll get minus 2C2 equal to minus 2. C2 equal to 1. So that is C2 equal to 1. From the equations, C2 equal to 1 means we know the value of C2, we'll find C1. C1 plus C2 equal to 2. That is C1 plus 1 is equal to 2. C1 equal to 1. C1 is also 1. Then we'll get, so substitute C1, C2 values in the equation number 1. Then the recurrence relation solution is an equal to 1 into 1 power n is 1 power n only. Then 1 into 3 power n is 3 power n only. That is an equal to 1 plus 3 power n is the solution for the recurrence relation. 1 plus 3 power n is the solution for the recurrence relation. So what we have discussed up to now, what is meant by generating function, what is the procedure to find the solution for the generating function, and we can understanding that the generating function by considering some example. Whatever the problems we discussed, all those are the second order recurrence relation. Second order relation means that is a power up to 2. That means we have to take up to 2 terms are present in the sequence. In the next video, we'll discuss about the 3 terms in the generating function. Thank you.